All right, as we move forward in exponents, the next topic we need to teach is scientific notation. Now, scientific notation is really something that's only useful in the field where science is being applied. We're really talking about things that are either really, really big or things that are really, really small. So the first part of this lesson is about numbers that are really large. And when we talk about large, we're talking about the number of stars in the galaxy, or perhaps the number of grains of sand on a beach, or maybe the entire bird population in the state of California. We're talking about numbers that are bigger than your everyday numbers. We're not talking about using it to talk about the number of cars that are in your parking lot at school right now, or the number of people that are in your class. So let's take a look at a situation where we might want to use scientific notation to talk about how much a blue whale weighs, or a gray whale, or a whale shark. These right here are standard numbers. A blue whale weighs 250,000 pounds. And if we want to turn that into scientific notation, I want you to focus on the point right there, right after the first digit that you see that's not a zero. And so I'm going to put a decimal point right there, and this becomes my number. Instead of 250,000, I'm going to represent this with 2.5. And then it's just a matter of counting. In order for me to put the decimal place there, when it really belongs out here after 250,000, I would have to move it backwards 1, 2, 3, 4, 5 places. And so since I had to move it back 5 places, that becomes 10 to the 5th power. So this is a key to scientific notation being written correctly. The number out here has to be between 1 and 10. Can't be a 2-digit number. Obviously can't be 250,000. That's why we called it 2.5. If I had moved the decimal here and called it 0.25, that would be too small. It's got to be bigger than 1, and it's got to be less than 10. And then this 5 tells me how many places I had to move the decimal. Let's take a look at the gray whale. The gray whale is 68,000, and I'm going to focus on that spot right there between the 6 and the 8, because that's the number I create that's between 1 and 10. So my new number out front becomes 6.8 times, and then the power on 10 is however many decimal places I had to move it. I had to move it from here. I had to move it 1, 2, 3, 4 places. So it'll be times 10 to the 4th. And then this whale shark, some people will stop here, but if I stopped here, it'd be 41.2, and that's not between 1 and 10, so it doesn't belong there. It belongs between the 4 and the 1. And notice that the number I get left with is not 4.1, it's 4.12. So we're going to keep 4.12. We got to keep all those non-zero digits, and then we just got to count spaces. So to get the decimal from here back to the 4.1, 2, we're going to go back 1, 2, 3, 4 places times 10 to the 4th. Now, as a general rule, you can see that these two exponents are a 4. This one's a 5. If they're all written in scientific notation, the bigger the exponent, the bigger the number. So a blue whale is larger than either of these numbers here. And then you can see this is a 4 and that's a 4. Well, when the exponents are the same, we just take a look at the numbers out front. This is 6.8, this is 4.12. So this right here is a bigger number than a whale shark, which is at 41,200 pounds. So let's take a look at one more example. If I had to write the distance from the Earth to the Sun, it's 93 million miles, and we're going to turn it into scientific notation, which means I need a number between 1 and 10, and it's going to be right there. It's going to be at 9.3. So I'm going to write 9.3 times 10 to the, and then we got to count spaces. The commas make it easy. That's 3, that's 6, one more would be 7, times 10 to the 7th. And since it's a word problem and it's got units, it's 9.3 times 10 to the 7th miles. Let's talk about going backwards. What if I already have a number in scientific notation and I want to turn it back into a standard number? So we're going to start with 3.5, and that times 10 to the 6 tells me that I'm going to be moving it 6 decimal places. So we're going to move this number 6 decimal places to the right, because it's a positive 6. It's a positive exponent. It's a really big number. So we're going to go 1, 2, 3, 4, 5, 6, and my decimal is going to stop there. We're going to fill in all these little bumps, these little valleys with zeros, and that's going to give me my standard form. And I'll count backwards, and I'm going to include commas. There's a comma there and a comma there. So this really becomes 3,500,000, and we do want to clean it up. We don't want to write it with all the bumps and all the scratch. So there's our number in standard form, the regular numbers we're used to looking at, 3,500,000. Now, we are going to run into some examples, and it's always a test of students in a math class, is what's wrong with this picture? Why is this incorrect? It looks like scientific notation, but if you take a look, 45 is too big. So my number is not between 1 and 10. We're going to take the decimal and move it one more place. So my new number is going to be 4.5 because that's between 1 and 10. And the question now is, what do I do with the power? Because it's not 5 decimal places anymore. So I want you to think about it this way. The decimal was right there, and I just made this number a little bit smaller. And if I make it out a little bit smaller, that power has to get a little bit bigger. Since I moved it one place here, I got to make the power bigger by 1, so it's times 10 to the 6th power. Here's an example of something that's the opposite. 0.54 is too small. It's not between 1 and 10. So the decimal really belonged right there at 5.4, and I have to move it one place. I have to make the number bigger by 1 decimal place. And when I make the number bigger, the power has to reflect that and get smaller by 1 decimal place. I'm going to take 1 away. So 0.54 really becomes 5.4, and the power is 10 to the 2. And you'll have a few more practice problems in your lesson when it comes to identifying an error and writing numbers correctly in scientific notation. Let's go take a look at a situation where we might want to practice problems in scientific notation with negative powers of 10. These numbers would be used for quantities that are very small. Now, we're not talking about small like, hey, I only have a few M&Ms left in my bag. I'm talking about something like, say, the diameter or the size of a bacterial cell, or, for example, the diameter across of it. This is a microscopic picture of a human hair, and here's a DNA molecule. So these are things, this is under an electron microscope. These are really, really tiny numbers, and they're going to have negative powers on our exponent for 10. So let's take a look at this number here. The principle still is the same. The number out front has to be between 1 and 10. So if I want to put a decimal here on this number of 0.000025, my decimal really belongs right there at 2.5. So the answer is going to have a 2.5 in the front for scientific notation. But the question is now, what's that power? Well, it's a small, tiny decimal. It's smaller than 1. It's going to have a negative exponent, and now we just count spaces. The decimal was here. I'm going to count to there. I got to go over 1, 2, 3, 4, 5 decimal places. So this is times 10 to the minus 5th, and it does have units. So we're going to give it units. It is a word problems, so it is meters. 2.5 times 10 to the negative 5th meters for that really tiny decimal for the diameter of a human hair. Let's go take a look at this problem. We're going to turn this one into scientific notation as well. I see my decimal here, and the decimal really goes, I can't put it before the 3, it's got to go after the 3 so that I have a number between 1 and 10. So my new number is 3. I don't have to include a decimal or anything else. There's nothing after the 3, and it's times 10 to the, and we're going to go ahead and put a negative sign because this is a tiny decimal and we're count spaces. 1, 2, 3, 4, 5, 6, 7, 8. So 10 to the negative 8 centimeters across as the average size of an atom. So we're talking about something that's pretty small. And when we talk about small numbers, they have tiny little decimals. What if we had to go the other way? What if I was already given a number in scientific notation? I want to know, what is that number written in standard form, which means we're going to get rid of this 10 to the negative 6, and we're going to expand the decimal out. So let's start by writing our number 2.33, and now I'm going to move it 6 places. So it's going to go 6 places, but it's going to go 6 places left. If I went right, I'd be making the number really big. And this is a negative exponent. It's a tiny decimal. So we're going to go 6 spaces left. We're going to go 1, 2, 3, 4, 5, 6. We'll put our decimal there. We're going to include Mr. Spring's 0 right there in front. We're going to include a bunch of placeholder zeros because this decimal is so small. We're not going to write our answer with all those little bumps. We will recopy it as 0.00000. And then we'll include our non-zero digits, 233. It was a word problem about the diameter of a blood cell, a typical platelet, and it was given in meters. So that right there is our final answer in standard form. We're going to get asked these kinds of questions about comparing size and the question of which one is larger, 2 times 10 to the negative 3 or 3 times 10 to the negative 2. Now, I noticed right away that they're both written in scientific notation. That 2 and that 3 are both between 1 and 10. So then all we have to do is look at the exponents. And which one's bigger? Well, a negative 2 is 1 bigger than a negative 3. So that makes this number here, 3 times 10 to the negative 2, larger because its exponent is bigger. But if you're not sure, you can always turn them into standard form. So 2 times 10 to the negative 3 would be a 2. And my decimal really is right there. And I'm going to go backwards 3 places. So it's right there. We're going to go backwards. 1, 2, 3. So this number in standard form is really 0.002. And this 3 times 10 to the negative 2, I'll put the 3 there. My decimal really goes right there after the 3. I'm going to go backwards 2 places. Once, twice, there's only 1 0. And you can see that the smaller the decimal, the more decimal places, the smaller the number. So this is larger. But it is important to understand that if things are written in scientific notation correctly, if there's a power that's bigger, that number is going to be worth more. It's going to be a bigger value. The last question we have in this lesson, which measurement would be least likely, meaning the one we wouldn't write in scientific notation? The thickness of a dog hair, the radius of a period on this page, or the ounces in a cup of milk? Well, the radius on this page is that tiny little guy right there, and that's not a normal number. I don't know what the radius is, but it's pretty dang small. And we already saw a picture of a human hair. A dog hair is not going to be a whole lot thicker, and under a microscope, that's still a pretty tiny number. Now, if we look at a cup of milk, I don't know if you can read these numbers, and some of this just comes from experience of seeing some of these things, but there's 2 ounces, 4 ounces, 6 ounces, 8 ounces, and a cup of milk has 8 ounces, and 8 is not something we would want to write in scientific notation. So since a cup of milk is like a regular number, it's not really tiny and it's not really huge, that's one that's going to be least likely to be written in scientific notation. Good luck with the rest of your lesson.